pretty tough exam in 2018, and I think statistically it was the hardest one ever. Question 1 from exam 2 is no exception. So let's pick it up at question F. State the values of A for which f of x is the same as p of x for all x. So here's p of x, and f of x was this one here. Notice the constant on this is plus 0. So if I go over here and note that my constant is a squared and equate that to the constant in the original problem, therefore a is equal to 0 by equating coefficients. Okay, find all solutions to p dash x equals 0 in terms of a where appropriate. Okay, so what we're going to do first of all is define a function. Okay, there's my function. So find all solutions when the derivative is equal to 0. So we're going to get the derivative function. Solve that equals 0 for x in terms of a. So we've got 3 zero gradient points, one at x equals 1, one at x equals negative a plus 1 take 1, and another at negative a plus 1 take 1, I presume. Yes. Okay, so there are my 3 solutions. Find the values of a for which p of x has only one stationary point. All right, so it might be timely now to actually have a look at what this function looks like on the calculator. So what I'm going to do is take a copy of that and go over to Graph and Table and paste it. And here it is. Okay, so it's defaulted to an a value of -7. All right, let's have a look and see what happens. So as I change these values of a, we can see what happens is we get a variety of different looking sort of graphs, right? And we want to find the values of a for which p has only one stationary point. All right, well, if we have a look, we're getting the one stationary point there, right? There's that one stationary point. All right, so when does that start to happen? Well, it looks like at values of a less than 0, we're getting 1, 2, 3 stationary points. So it's going to be somewhere around here that it actually happens. Now, how are we going to find out? Well, what we're going to say is this can't be changed. There's nothing we can do about the stationary point x is equal to 1. So let's say that that is going to be the stationary point, which means, is there a way that I can void these two stationary points? That is, would a value of a make both of these solutions not exist? And the answer is in trying to find a value of a for which the square root of it would be null and void or undefined. And so we're going to say that let's see if we can make negative a plus 1. What we want to do is see if we can make it less than 0, okay? And that'll mean that we attempt to find a square root of a negative number, which doesn't exist in the real number system. So negative a less than -1, a greater than 1. And so it's going to be for values of a greater than 1 for which we only get the one stationary point. And that seems to be reflected in what's happening in the graph over here. So when a is equal to 1, when we drop it down to less than 1, we're getting the 3 stationary points. At 1, we're getting the 1 stationary point, which is a bit further south. Let's see where that happens. It's like min, let's change that to -20 and see if it appears. Yeah, there it is there. So again, we'll just regraph that. So there is 0, 1, and it seems like we're just getting the one stationary point there. Find the minimum value of p when a is equal to 2. Okay, Now, what we're going to do is go back into the main section, and I'm going to do f of x with a equal 2. And there's the new f of x. So what I'm going to do is I will diff that function, solve it. So what I can presume is that there's only one stationary point, so that's got to be its minimum. And therefore, what I'll do is take this with a is equal to 2 and jam x equals 1 into it. And it's going to give me my minimum value, which in this case is negative 13. That's all we need for that one. We only need to write down negative 13. If P has only one stationary point, all right, and we've established the values of A for which P has only one stationary point up here. So this is important, this question. So it's when A is greater than 1 that this is going to happen. Find the values of A for which P of x equals 0 has no solutions, okay? i.e., that's going to be like a parabola that's up there, has no solutions, okay? So we want to send P of x either above or below the axes, and just by looking at the graph before, it's going to be above. So we want to find the value for which that occurs. Let's go back and have another look at the function again. So go back to graph and table, and let's hit it here. And notice that somewhere between 6 and 7, this graph pops above the x-axis. So here's 1. So the value of A we know has to be larger than 1. And then what we're going to do, if we increase these A values here, it goes lower and then it starts to come up. So somewhere between 6 and 7 is going to be the value for A. Now, what's it going to be exactly? Well, let's go back over to our main screen and find out. Okay, so the way we're going to do it is I've got P of x. So let's just remind ourselves what f of x is. All right, now that's interesting. That's f of x, and I defined it as this function here. So here's a bit of a problem with using parameters on the calculator. What's happened is that A has been stored from the graph that I've used before. So A has been stored as 6. Okay, so what we're going to do is action. Let's see if edit and clear all variables is going to help us. A is equal to A. Now let's call f of x again. And there it is in the form that we want. So what we're going to say is we're going to do solve f of x equals 0 for x. Okay. Now what we're going to do, I'm not going to do that. I'm going to say that I know the stationary point occurs when x is equal to 1. Okay, so that's important to note. So what we're looking for is when P of x is more than 0. So we want to send P of x up. We want it to be more than 0. And the value of x is equal to 1. So at x is equal to 1, that's where the stationary point occurs. So let's do that first of all. So I'm going to do f of x on the calculator with x is equal to 1. And that's what I've ended up with. I've ended up with this function here, okay? And what I want with this function here, I'm just going to expand it. So when P of x is larger than 0, when x is equal to 1, we get a squared take 6a take 5. We want no solutions, okay? So we want the values of a where it has no solutions, okay? So what we're going to do is we want this to be less than 0, okay? So this one here, we're going to let the new function form to be less than equal to 0. So again, I'm going to go back over to my calculator and I'm going to go solve for when it's equal to 0 for x, for a rather, and we get 2 solutions. So what it's basically saying is we've got an upright parabola, and one of them, negative 14, what's that like? It's like 3 point something, negative 3. So it's like there, like a little bit less than negative 1, and 3 is like 6 or 7. So here's like roughly our parabola. And what it's saying is it's less than 0 between these two values. Okay, it's going to be greater than 0 for the values less than that, and greater than 0 for the values larger than that. Now, what we're going to do also is note that A we know is already greater than 1. So we're going to forget that that one is there and only take this one here. And that's going to be this solution here. So we're going to say A is equal to negative root 14 plus 3. So we're going to go a plus minus on that, but A greater than 1, therefore A equals root 14 plus 3. Now that's roughly 6 point something, which again, back on our calculator, we knew that that would happen. So we go to graph and table and use the parameters one to do this. Somewhere between 6 and 7, we get this value here, or this stationary point going above the x-axis, or for a value of y greater than 0. So 6, there's 6, and there's 7 above it. So somewhere between 6 and 7 that occurs. Where is it exactly? Root 14 plus 3.